Question 34, the action of a catalyst. This is important. We know it lowers the activation energy, but has no effect. We better read the notes. Has no effect on the yield. So the effect is always increases rate forward by same amount. Not immediately obvious from the energy profile why this is true, but it is true. Increases the rate forward by same amount as rate back. You can't speed up one without speeding up the other. That would make sense. You've lowered the activation energy. But the fact, KK, is that it always speeds up the forward by the same amount as it speeds up the rate of the back reaction. So no effect on the yield, on the amount of product. You just get the product faster. No effect on the amount of product or on H values of reactants or products. Remember what it did to the energy profile? Lock that in. Reactants, products, activation energy, catalyst. What did a catalyst do? Lock it in, lowers the activation energy, and that's it. No effect on enthalpy, therefore no effect on delta H, just gets the products, whatever you're going to get, faster. And I'm sorry, that's pretty much all I've got time for. I think, however, there was one small problem with question 34, and I need to fix that up because this is your classic SAC question. It's your classic VCAA question. Every so often, they throw one of these graphs at you and they say, tell the story of the graph. What happens? I wish they hadn't done it. This, a VCAA question would always say goes up to there and then comes down. That's just coming down, that's coming down. That's an easy one. At that change, Cl2 was added. Now that's the easiest change. Clearly, the graph story tells you Cl2 went up instantly. CO and CoCl2 were not affected. We would expect that if you add Cl2, they will come down. How can they come down? By forward reaction. So if Cl2 goes down, CO has to go down. Note, that would have to be X. That would have to be X to get the stoichiometry right. And for every one of each of them, you get one CoCl2. So it doesn't quite look like it on this graph. Label it with an X, and then you've thought about the stoichiometry. The last one, Cl2 up, CO up. That one, CoCl2 down. Obviously, the back reaction was favoured. Why? All right, why would the back reaction be favoured? There was no initial change in concentration of anything. And note that on a graph, that implies there was a temperature change. So why would it have favoured the back reaction? The back reaction is endo. So why would it favour the reaction that would decrease the temperature? Implies you increased the temperature at the 40-second mark. So that's the second change. Increase the temperature, increase T. First change. Now the second one, all the concentrations went down. All C's down instantly. There's only one way all of them could go down. You're not going to have just taken out, you could theoretically have just taken out bits and pieces, but it's much easier for all of them to go down if you increase the volume. Now just check that the directions are right. If you increase the volume, that would decrease the pressure. system tries to increase pressure. Now, favour a reaction with more mole. Which more mole? 2 mole, 1 mole. Okay, it can increase the pressure if it favours the back reaction. And if it favours the back reaction, yep, back reaction favoured. So the response to the change, I'd rather it had gone down, but let's now just do this mathematically. We take that down to there. Now, just looking at that graph, that is roughly about a 20% decrease in concentration, which I would say implies about a 20% increase in volume. So it might have gone from, say, 100 mils to 120 mils. That would explain why the concentration has dropped by 20%. But if that concentration goes down by 20%, the other concentration should have gone down by 20%, by 1/5. Does that look like it's gone down about 1/5 of its original value? Here's its original value. There's its value after the change. That looks about 1/5 lower. You could get out a ruler and correct me on that one, but I'm estimating that's about 1/5 lower. So a 20% decrease in the concentration. All the other concentrations should have decreased by 20% as well. So take this one down to 1/5 of what it was. Take this one down to 1/5 of what it was, approximately. And that's then in proportion. So I don't like these changes for a start not being instantaneous. A VCAA exam would always be instantaneous. If this now goes up by X, then this will go down to there and then go up by X, because you can't make one Cl2 without making one CO. And this one will go down by X, so that it's stoichiometrically in proportion. So I'm sorry about that. The drawer of this graph did not consider the relative effects. It's definitely a volume change, and the volume change looks like about a 20% increase in volume, which would drop the concentration by about 1/5 of what it had been. Not to 1/5, by 1/5 of what it was, 20% lower. So all of the concentrations would go down by 20%. Now that's the sort of picky thing a teacher might pick up on a SAC. It just might be picked up on a VCAA exam. So are we clear about that? This is a really good question to look at, but you need to have fixed it up. That is definitely the easiest change to pick. Really, a VCAA exam would just have it going up, just the Cl2 going up, and no instant change to the other two. Okay, this thing that went up was added. Then you check with Le Chatelier's principle. It should have been removed, but not back to where it came from. Yes, that makes sense. And then get the stoichiometry down by X. This one will go down by X. That'll go up by X. Easy change. Second easiest change is this temperature change, where no concentrations instantly change, but there's a readjustment to a new equilibrium. That's your signal. It's a temperature change. No instant changes to any concentrations, but at a different temperature, you've got a new K value. That's why it's out of equilibrium. No instant changes to the concentrations, but you've got a new K value. So your concentration fraction doesn't equal your K anymore because there's a new K value at a different temperature. That's tricky to explain, but easier with the logic. You can see that the back reaction was favoured as the reactants went up and the product went down. Why would the back reaction have been favoured with a temperature change? It must be because it's favouring the, clearly favouring the endothermic direction. Forward is exo, back is endo. Why would it favour endo? Because it's trying to cool things down. You must have raised the temperature and it's fighting you. And then look for all of the concentrations either going up, all the concentrations going down, but hopefully in the right proportions. If you double the volume, all concentrations will halve to what they were at the instant you changed it. If you halve the volume, all concentrations would double. Inverse relationship between concentration and volume. Don't forget that C is inversely proportional to volume. So you can't have them going down by the same amount if they're not starting at the same value. They'll go down by the same fraction. This one looks like it's gone down to me by about 1/5 of what it was, down about 20% of its value. So if this was 100, it's gone down to 80. But if that's gone down by 20%, then this should have gone down by 20%. So if this was starting at 60, what's 20% of 60? That's what it should have gone down by. And if this was, say, starting at 30 and it's gone down by 20%, then it should have gone down by 20% of 30. It'll be a smaller drop than this bigger drop. They should be the same percentage drops because it's the same percentage volume change. And that, I think, is all I wanted to look at, because the last 3 or 4 questions are to do with rate time graphs, and we've covered that.